Earlier, we briefly touched on the idea that calculating the theoretical amount of product we should expect helps us evaluate the quality of the chemical reaction that we've carried out. No chemical reaction is perfect. Material is always lost in some way, shape, or form, or in some way, shape, or form, impurities are introduced into the final product. Percent yield is a quantity that captures the percentage of the theoretical amount of product that was actually obtained. And while percent yield is almost always less than 100%, in some cases where impurities have been introduced, the percent yield can actually be greater than 100%. So there are two big steps to determining percent yield. The first is to calculate the theoretical moles of product that we'd form, assuming complete consumption of the limiting reagent. So this is a general statement, general in the sense that it applies even under situations where there's a limiting reagent. If there is no limiting reagent, then we can use any of the reagents to calculate yield. But when there is a limiting reagent, we don't want to overestimate the theoretical product, and so we need to use the limiting reagent as a basis for calculating the theoretical moles of product. Step 2 is to divide the actual moles of product obtained by the theoretical moles from step 1, and this may require us to convert a mass of actual product measured in the laboratory to a number of moles. But once we've got moles actual and moles theoretical, we simply divide the actual by the theoretical, and this will give us a decimal value. Multiplying that by 100% provides the percent yield of the reaction. A brief note about significant figures and yield. Although it's common to have a large number of significant figures in measured masses, it's prudent practice to use only 2 significant figures for yield. And the reason for that is yield is variable. There's a huge imprecision that comes with yield, not because the masses measured are imprecise necessarily, but because the amount of product actually obtained and the manipulations to obtain that product, the purification, things like filtering, the isolation, extraction, crystallization, all of these processes are imprecise and depend on error that the experimentalist might introduce, as well as the particulars of the lab room that day, the particulars of the glassware used. All kinds of things figure into variability in yield. Because of that huge variability, it's prudent only to use 2 significant figures in yield. And that means basically reporting yield only to the ones place and never using a decimal in yield. So where you can, avoid yield figures like 94.5%. The 0.5 is meaningless in the sense that if I were to go run that reaction after seeing that yield and I got 93% instead of 94.5, that could be due to just natural variations in the glassware I'm using or my technique. A less significant figure like 95% gives a more realistic view of variabilities in the yield. So let's look at an example of how to calculate yield. Imagine we started with 6.74 grams of copper metal and we actually obtained 3 grams of water. The theoretical mass of water that should have been obtained can be determined using a dimensional analysis process very similar to the one we've seen before. We start in mass land with the mass of copper, convert that to a number of moles, use the molar ratio of copper to water, or really water to copper, to convert to a number of moles of water, and then get back to a mass of water using the molar mass of water in the final step. And that's exactly what you see in mathematical form below. We start with the 6.74 grams of copper in mass land. We move to mole land by dividing by the molar mass of copper. Then we use the molar ratio of water produced to copper consumed, 2 moles of H2O per 1 mole of Cu, to get to moles of water, and then finally multiply by the molar mass of water, 18 grams per mole, to get to the theoretical amount of water that we should obtain if all of the 6.74 grams of copper are consumed. One of the principles behind yield is all of the reactant may not be consumed. Some of the reactant may remain unreacted. To determine the percent yield, we can take that mass that we actually obtained, 3.00 grams, divide by the theoretical mass, and multiply by 100 to get a final figure of 79%. And note the 2 significant figures. I'm not using decimals here, even though I could, right? I'm quote-unquote allowed to use 1 additional significant figure. But variability in experimental technique makes yield a very imprecise statistic. One other thing to notice about the way yield is calculated in this example is that I'm using masses instead of moles, and this is perfectly fine as long as you make sure to use the same quantity in the numerator and denominator when you're calculating yield. You can use moles or you can use mass. When you're in the laboratory, it's often more convenient to use mass because you'll be making mass measurements, but on paper it can be more convenient to work with moles, and you may have a personal preference one way or the other. Either way is fine and you'll get the same numbers, and I would encourage you to test that for this example. See if you can determine the theoretical number of moles of water that you ought to obtain, and then convert the 3 grams to moles of water. Take the ratio of the actual moles to the theoretical moles and see if you still get 79%.